Students, today in this lecture we will discuss about the concepts of phase velocity and wave packet. Students, we know it very well that according to de Broglie's hypothesis, a moving particle is associated with waves which are known as de Broglie waves or the matter waves. If matter waves are there, what is the equation which can represent a moving particle? So a simple plain monochromatic means single color or wavelength. Monochromatic wave is, we are taking it in one dimension, y as a function of x and t, it is equal to a exponential iota kx minus omega t. Here a is the amplitude of wave and k is the magnitude of propagation vector k, and it is equal to 2 pi by lambda. Lambda is the wavelength of wave and omega is angular frequency, that is equal to 2 pi nu. Nu is the frequency of wave. So the question is, does this single wave train can actually represent a moving particle? And for that we define the phase velocity or the wave velocity. So phase velocity is the velocity with which a point of constant phase travels in the medium. For example, when we threw a stone in the pond, then ripples are created on the surface of water. And the disturbance spreads in the form of concentric circles. If we choose any circle, then water molecules on that particular circle are vibrating in the same phase, which is constant. And the velocity of water molecules having that constant phase is known as the ripple velocity. Similarly here, for a point of constant phase, we have to calculate the velocity, and the velocity of that point is known as the phase velocity. So for example, in this equation for the wave, kx minus omega t is the phase of the vibrating particle. It is denoted by phi kx minus omega t, and this is equal to constant. We differentiate it with respect to time, that is k dx by dt minus omega is equal to 0. Here dx by dt is known as phase velocity v, ph, or wave velocity, minus omega is equal to 0. So this gives us phase velocity is equal to omega by k. Or this is equal to, if we put omega and k, so we get 2 pi nu upon 2 pi by lambda. This cancel. So this is frequency multiplied by the wavelength. Now if you multiply it by Planck's constant in the numerator and denominator, then we get h nu divided by h upon lambda. H nu is the energy of the particle corresponding to frequency nu e, and h by lambda by de Broglie's hypothesis is the momentum of the particle. Now by theory of relativity, E can be written as mc square. M is the mass of the particle, c velocity of light, and p is the momentum, mass into velocity. The mass is cancelled, so this is c square by v. Now c, velocity of light, is much greater than particle velocity v. So this relation implies here that phase velocity or wave velocity is greater than the velocity of light. Now since velocity of light c is greater than the particle velocity, so we can write phase velocity is greater than velocity of particle, because c, velocity of light, is greater than velocity of particle. Now what does it mean? It means wave velocity or phase velocity is greater than particle velocity. The wave travels faster then the particle and particle lags behind. It means a single wave train cannot represent a moving particle, because if the wave has to represent the particle, then the wave velocity must be equal to the particle velocity, but they are not equal here, because phase velocity is greater than particle velocity. Now, this problem that single wave train cannot represent a moving particle was resolved by the Schrodinger, and he said that a moving particle has to be represented by a group of waves which is known as the wave packet. A wave packet consists of a group of waves, each with slightly different velocity and wavelength. The phases and amplitude of the waves so chosen that they interfere constructively over a small region of space where particle can be located, and outside that region there occurs the destructive interference and the amplitude becomes zero rapidly. Now, to understand the interference among the waves in the wave packet, we take the example of the phenomena of beats from sound, and we consider two waves of nearly the same frequency, of frequency 48 Hz and second of frequency 56 Hz. Now, according to the phenomena of beats, when two sound waves of nearly the same frequency superimpose, then the intensity of the resultant wave becomes alternately maximum and minimum. Now, here we have taken the two waves of nearly the same frequency, one of 58 and the other of 56 Hz, and we have plotted graphically here. Time is along x-axis. Now, from the first source, it is emitting 3 waves in 1/16th of second, and it is emitting 6 waves in 1/8th of second. For second source, that is for 56 Hz, the source is emitting 3.5 waves in 1/16th of second and 7 waves in 1/8th of second. Now, if we check their superimposition, then at 1/16th of second, we see that waves are meeting in opposite phase. Here the wave is moving upward, here the wave is moving downward. The amplitude of the wave is reduced. At 1/8th of second, we see that the waves are meeting in same phase, and the amplitude becomes maximum and intensity also becomes maximum. So, after every 1/8th of second, there occurs the maximum in the intensity of the resultant wave, and the bit frequency is nu2 minus nu1, that is equal to 8 Hz. Similarly, in case of wave packet, there occurs both constructive and destructive interference. Constructive occurs where the particle can be located. The behavior of a moving particle is described by a function psi xt. We are taking it in one dimension, and it is called as wave function. Now, this wave function is related to the likelihood or probability of finding the particle in a certain region of space, say at position x and at time t. Now, how a wave packet is constructed from a large number of waves, that we will discuss in the next lecture. So, thank you students for listening.